So now I'm gonna do my game theory project presentation. My project is application of zero-sum dynamic game theory to robotic path planning. As it shows, this project is about how to use the knowledge of game theory to solve optimization problem in control system. My director professor is Chunyuan Zhu. First, since my object is AGV, so I'd like to start with the basic introduction of AGV. What's AGV? It's short for Autonomous Ground Vehicle. It's kind of autonomous vehicle or robot controlled by control systems which can explore the environment by itself. So it is obvious that the core technique of it is path planning. Why I choose AGV as my project is because it's wide spread in many areas and has a big market in health service, industry, military, and space exploration. Especially in industry and in military, there are many factories using this kind of EGV to make the production more efficient. Also, for military in the USA, government use EGV for detection tasks. There's one thing worth to mention. Many countries are studying on a kind of non-human in AGV, which can hold nuclear weapon, acting as a self-exploration car. This project has four core modules: the navigation and location, control system, sensor technology, and path planning algorithm, in which the control system and path planning algorithm are what I focus on. There are two main achievements for this project. First is the development of control system structure, and second is the development of path planning algorithm. So first, let's talk about the control system structure quickly because it's not the main point of this project. This is a traditional control system, which is a closed-loop control system. It starts from the sensor. The sensor gets information from the environment, and the microcontroller made the environmental perception and the environmental modeling. Then we can do the path planning. After calculating the result, the execution and motion system will get and give the get the information and give the feedback to the environment to make the AGV act appropriately. There is an obvious shortcoming of this system that the fault tolerance is very low, which means that once one part of the system breaks down, the whole system will be paralyzed. So to solve this problem, I develop a new control system like this. We can say each part of this system can make a complementary for each other. So this system can easily make up the mistakes that be introduced thoroughly. Sensors are the input of the system. They are the perception unit which can perceive the environment and the car itself's information. The environment map is the core of the control system. The result of all the information can come from this part. Its basic element includes the environment map, robot location. It not only have effect with the motivation control unit and location unit, but also communicate with the base of the system directly. Then the location model implies the location function of the system. The output is a coordinate of the plane and the angle of movement of the car. The path planning module is the core module of the system. It synthesizes the information of the location and the environment and find a way without block. It's the upper module of the control system, which is the key of avoiding obstacles. The behavior control module's main task is to synthesize the environment information and the result of the path planning to order the motor. The system structure is to proceed the integrating and the decomposing of each module. So an appropriate system structure is the basic of autonomy and real-time. Then we come to the main part of the project. It's path planning. There are several ways to realize this function. Variable map, artificial potential field, fully logic algorithm, generic algorithm, and then finally robust control. So what we're gonna talk about is the robust control because we can use game theoretic foundation to deal with this issue. First, we need to know what is path planning problem. We got to know it from its components. It has 5 components. First, a 2 or 3-dimensional including space, and second, a rigid or multi-body robot that is completely described using polygonal, polyhedral, or algebraic models. And third, a configuration space. And fourth, static obstacles. And fifth, initial configuration and goal configuration. Then the next task is to consider how to transfer the path planning problem to motion strategy problem. The figures show some basic issues in path planning, like manipulation strategies, non-harmony and dynamics, active sensing and visibility, and so on. The general motion strategy problems encompassed by the game theory framework can be viewed as a generalization of the basic path planning problem, but it will have more complications and components. Then we need to struct to then we need to build the motion strategy problem. We know that one of the most common ways to handle difficult engineering problems is to use modular reasoning. It is always tempting to reduce a large problem into sub-problems, such that if each sub-problem can be solved, a solution to the original problem can be assembled. We can typically divide the motion strategy problem into 3 modules. First, a path is computed, then a trajectory is determined, and finally, a tracking controller is used to follow the trajectory. We can see the procedure thoroughly from this figure. From word representation to output a motion strategy. Then we need to formulate the motion strategy problem. The motion strategy problem can be modeled as a dynamic game that is played with one or more decision makers, which could correspond to robots. And the special decision maker called nature is capable of interfering with game, ultimately leading uncertainties in prediction and sensing. The goal within this framework is to design a strategy that optimizes the choices of the decision makers under all possible contingencies with which they could be confronted. Game theory can model a situation in which some decision makers represent disturbances that must be overcome by the other decision makers. Such problems can be viewed as a game against nature. If the uncertainty is represented probabilistically, the game against nature becomes a problem of stochastic optimal control theory. So we're gonna start with the components of the motion strategy problems, as what Professor Zhu usually does. From item 1 to 6, the components corresponds to the state, transition, and control. For example, an index set N means N decision makers, and an index set K means denotes the state of the game, and the site X called the state space. A site UKI defined for each K is called the action space, and the site theta Ka is called the control action space for nature at stage K. And the function Fk defined for each K belong to big K is a state transition equation. From atoms 7 to 11, the components correspond to sensing uncertainty. For example, a site YKI is called the sensor space, and the site theta KSI is called the sensing action space. The function HKI denotes the observation equation of the ith decision maker concerning the value of xk. The atom 12 corresponds to the strategy concept. Atom 13 corresponds to the encoding preferences. Then we need to know how to compute optimal strategies. The algorithm description is organized into 3 parts. First, the general principle of optimality is described, which greatly reduces the amount of effort that is required to compute the optimal strategies. The next part describes how cost-to-go functions are computed as an intermediate representation of the optimal strategy. The third part describes how the cost-to-go is used as a navigation function to execute the represented strategy. First, is exploiting the principle of optimality. For example, there is a probabilistic uncertainty in predictability resulting in the state transition equation. The actions for nature are sampled from the probability density. Using this model, probability density function can be derived for next states of the form. The task is to design a strategy that optimal in the expected sense. For example, suppose that there is a probabilistic uncertainty in predictability, resulting in the state transition equation xk plus 1 equal to f xk uk theta k. The actions for natures are sampled for the probability density p theta k. Using this model, a probability density can be derived for the next state of the form p xk plus 1 xk uk. The task is to design a strategy that is optimal in the expected sensing. In this case, the cost to go is defined as lk star xk e the e blah blah, in which the e denotes the expectation taken over the actions of nature. The dynamic programming principle is lk star xk, which is analogous to the lk star. Other variations include finding multiple Nash equilibrium, worst case strategies, and determining cost to go functions directly on the information space when there is uncertainty in sensing. Here is the second part of an optimal strategy can be computed by successively building approximate representations of the cost to go function. One straightforward way to represent a cost to go function is to specify its values at each location in a discretized representation of the state space. Note that this requires visiting the entire state space to determine a strategy. Also, this is normally unacceptable for a basic path planning problem. For the extensions considered in this paper, the solution is a feedback mapping instead of a fixed path. Since the strategy must produce an appropriate action from any state, it is quite reasonable to visit the entire state space. Additionally, note that the cost-to-go function is encoding a globally optimal solution, which must take into account all of the appropriate geometric and typological information at a given resolution. Artificial potential functions have often been constructed very efficiently in path planning approaches. However, these approaches heuristically estimate the cost to go and typically prone to have local minima. Then the third part is using the cost to go as a navigation function. To execute the optimal strategy, an appropriate action must be chosen using the cost to go representation from any given state. One approach would be to simply store the action that produced the optimal cost to go value for each quantized state. And the appropriate action could then be selected by recalling the stored action at the nearest quantized state. Once the optimal action is determined, an exact next state is obtained. This action continues until the goal is reached or a termination condition is met. So those are the three parts of formulating the motion strategy game. After that, what we should do is to connect the strategy motion game to the robotic system. So this figure shows a conceptual relationship between robotic hardware and software that provides some kind of motion strategy that controls the hardware. The strategy is the actuator input to the robotic system, and the robotic system gives sensory output feedback to motor strategy. Then the motion strategy can deal with the information and give it back to the actuator again, which forms a closed loop system. In conclusion, game theoretic foundation can be a useful way to improve my algorithm of microcontroller to deal with the core function path planning. It's also an important issue to know how to transfer it to the computer code. So the last step is to program the theory, making it realistic, as the theory is always auxiliary. What makes the technology and the society progress is a reality. That's all. Thank you for listening.